Okay, thank you everyone for coming back. I apologize again for the coffee scandal, coffee gate. Hopefully, I'm going to do what I can so that Wednesday it does not recur. So this will be for our final talk of the day. We're staying in the theme of spectral theory of Schrodinger operators, and so Schach Møller, I apologize if I am very badly mispronouncing your name, will be speaking to us about high energy clustering of eigenvalues for Schrodinger operators on the cubic metric graph. So thank you very much for.
Well, thank you. And keeping in the theme of the last talk, let me thank the organizers, both the localized ones and the delocalized ones. And also congratulations on your birthday. When I visit you next year, I hope we will be discussing problems over cappuccino again. Yes, that's right. I mean, we have been discussing over copious amounts of your own coffee from your office, but it's not exactly the same. Okay, so I'll talk about some joint work here with Evgeny Kochayev, who's now in China, and Morten Grud Rasmussen, who's in at Aalborg University, north of So the cubic metric graph, let me explain what that is. So there are some drawings here. It's easier to draw than to write. So here is a part of a 3D, three-dimensional cubic metric graph, but let me draw it in 2 dimensions here on the blackboard. So you have a grid here. And on the vertices you have, in here you have set 2. Well, then you include all the edges between the vertices in set 2, so you get this grid. So you can of course do that in any dimension. I should say dimension 1 is not so interesting because you just get the real line. So you have to be at least in dimension 2 to have something new to talk about. So inside the metric graph here, we have a unit cell, which is just, you fix one point here, and then you just take 2 neighboring vertices in one direction. And you should really think of it as a fundamental cell. So when you move out along the edge, you really loop back to the origin. You loop out here, you loop back to the origin. So this is sort of the fundamental cell in 2 dimensions down here. So up here is a fundamental cell in 3 dimensions. Okay. So there was sort of a natural Lebesgue measure on these objects. So you have LP norms of functions on this cubic metric graph. And you can, of course, think of LP as a sequence space over the integer lattice with values in capital LP on the unit cell like that. And if you think of this representation of the functions as sequences of functions on the unit cell, you can have mixed LPQ spaces where you have, for example, inside here, you have a local LQ property. So on each edge, basically, the function has to be LQ. You can take the LQ norm over a unit cell that will form a sequence, and that you can ask to be LP. So that's these mixed LPQ Banach spaces. So that you can think of as a small LP as a sequence with values in LQ of a unit cell. So the metric Laplacian now is an unbounded operator on L2 on the metric graph. So you basically define it by just on each lead. Here you have an interval from 0 to 1 basically, and you just take the one-dimensional Laplacian on each edge. And then in order to get a self-adjoint realization, you have to impose boundary conditions on each vertex here. So there are of course many different ways you can impose boundary conditions on a vertex to get a self-adjoint realization. There are books written about that, about how to do that. So we picked sort of maybe the most natural one called Kirchhoff boundary conditions, which means that if you sum over all the still at a vertex, you sum over all the incoming derivatives and the derivative from one side and the derivative from the other side, you should get the same. And of course, if you're in one dimension, you can still do all that. What the Kirchhoff boundary condition will just tell you is that the function has to be differentiable across each integer. So you just get the normal Laplacian if you're in one dimension. So the spectrum of the metric Laplacian is a half line. So it's not so unusual for Laplacians, unless it's the discrete Laplacian. So we have 0 here. But what is perhaps a bit strange is that you have embedded eigenvalues of infinite multiplicity. So they said here that there is one at pi square, and there's one from a 4 pi squared, and then they come with larger and larger spacing in between. They're called flat bands at the clear eigenvalues. So flat bands, I'll come back to why they're called that. So the clear eigenvalues is because they can be built from the clear eigenfunctions. So let me make a drawing of that. So suppose you take sort of an elementary loop in here in the metric graph. You take a plaquette and then you walk around. Then you can insert the clear eigenfunction on, for example, the first clear eigenfunction up here. And you can switch sign to get the Kirchhoff boundary condition satisfied here. And switch sign again here, and then switch sign over here. And because you do that an even number of times, it maps off. So in that way, you get an eigenfunction. You put it 0 on everywhere else. So you'll get an eigenfunction corresponding to the first Dirichlet eigenvalue. And of course, you can do this in around any plaquette in the lattice, and you will get an infinitely degenerate eigenvalue. And if you use higher order Dirichlet eigenfunctions, then you can get all the other ones up here. So that's how. Yeah, so 2 pi. So, okay. So that's that. Now, as a Schrödinger operator, we just take you take a potential V. It's locally L2, such that you can. It makes nice sense as a multiplication operator. So you can start out with continuous functions and multiply them. Or globally LP. So on each unit cell, you have a finite L2 norm, and you can sum up the p powers of the L2 norms. You can perturb the metric Laplacian, and you can use Cato-Alec to construct this operator as a self-adjoint operator. Okay. Now suppose you choose a particular potential here, a potential that is only non-zero on an elementary loop like this. And on this loop, it takes some value kappa. Now, if you take the Dirichlet eigenfunctions are constructed here, they will still be eigenfunctions of the perturbed operator, but you will be pushing the eigenvalue with kappa. Right, so you will, for example, get a simple eigenvalue shifted here with kappa. So you can construct, by adding perturbations, you can construct and push out embedded eigenvalues from the Dirichlet spectrum. And of course, if you take a potential that has a different value of a disjoint plaquette somewhere, then you can push out 2 eigenvalues and so on. You can actually push out countably many eigenvalues of finite multiplicity with an LP potential with P not infinity. They will then all convert. They will have the Dirichlet eigenvalues as point of convergence. So maybe as an embarrassing aside, these examples here simultaneously pulls out eigenvalues of all Dirichlet bands. I don't actually know of an example that, say, pulls out an eigenvalue here, but doesn't do anything to the other bands. That may not be a coincidence, but I don't know. So maybe that's a nice little question to ask. Okay, so then comes the main theorem here. So forget about the conditions, maybe except that we're in dimension 3 or above. Forget about the condition on the exponent p. So what this statement tells you, it tells you where the pure point spectrum of the perturbed Schrödinger operator can be at least above a certain energy lambda. So there is some cutoff. Here we are not talking about what's happening below, we're talking about what's happening above. So the pure point spectrum has to be in some intervals around the Dirichlet eigenvalues. So there is some and the size of this window is uniform in energy. So the size of this window scales with some constant r times the LP2 norm of the potential. So this, so the window is uniform in energy. Remember, the gap between the Dirichlet eigenvalues increases, but the size of the localization does not. So this is what I mean at the title by high energy clustering. That we can say at high energies where any point spectrum has to be, if there are any, apart from the Dirichlet eigenvalues themselves. I should say, to tying with the previous talk, same goes for the singular continuous spectrum. That will also be sitting inside the same set if there is any. And there's sort of a general argument going back to Kuroda that will tell you that the singular continuous and the pure point spectrum is sitting inside a set of meshes. So general. Okay, so that comes down here. So what is capital lambda here? If the p norm of the potential is sufficiently small, then there's no restriction. So then this cutoff here isn't there. The theorem will go for the entire spectrum. Above a certain p norm, you have to go above something that scales almost like the p norm. But there is a logarithmic correction. So something like the p norm times logarithm to the p norm. So above that energy, you get this. And you can also quantify this lambda zero here, but I haven't done it. Okay. So is the statement of the theorem sort of clear? Okay, so then there is the restriction on the p up here. That looks a bit bizarre, but that comes from some input that we use that carries requirements and some p exponents. I'll come back to that later. Okay, so the proof goes via the Biermann-Swinger principle. So let me explain what the Biermann-Swinger operator is. So if we have a potential V here, we can factorize it into the square root of its absolute value. And what remains in order to get a factorization, we'll write V as U times V. Then if V is in this LP2 class, then the weights U and V will be in L2P4, so locally L4, with 4 norms that are 2P summer. And then we can define here for zeta in the upper half plane a weighted free resolvent, where we take the free resolvent of the metric Laplacian and weight essentially with the square root of the potential on both sides. So that's the Swinger. Now, one may show that if you're away from the Dirichlet spectrum, then you can take the limit when zeta goes to the spectrum of this Biermann-Swinger operator, you get a limiting object here. So since star here is just the integers minus 0. That's because there's no eigenvalue sitting down here at the bottom. Okay, so a key observation, which is well known if you're sort of familiar with Biermann-Swinger, that if you take lambda here is a real number which is not in this p set star, such that lambda squared is an eigenvalue of the Schrödinger. then 1 will be an eigenvalue of the Biermann-Schwinger operator. So if you want to rule out eigenvalues of the Schrödinger operator, what you can try to do is to rule out that 1 can be an eigenvalue of the Biermann-Schwinger operator. And a sort of obvious way of trying to do that is to take the operator norm of the Biermann-Schwinger operator and try to make it smaller than 1. Then certainly 1 cannot be an eigenvalue. And that's sort of the strategy. Okay. So for that, we need estimates on these weighted resolvents that are uniform as you approach the spectrum, such that you can obtain estimates on the limiting object. Okay, so here we have the following theorem. That if you take 2 weights, U and V, that are in L alpha 4, so alpha you should think of as the 2p from before. So the requirement up here corresponds to the requirement on the p in the main theorem. For all theta in the upper half plane, the operator norm here is bounded by this expression, where you have a logarithm divided by 1 over the norms of theta. So it's not an uncommon type of high energy estimate to have a 1 over the norm of theta, but there is a logarithmic error here that comes from the Dirichlet eigenvalues. And then there is a distance to the nearest Dirichlet eigenvalue. 1 over the distance, so it blows up. The estimate naturally blows up when you approach an eigenvalue, which is not unusual. And then out here we have the L alpha 4 norms of the 2 weights. Now, if you have this estimate here, then you can look at try to look at the contribution coming from the first part here and the contribution coming from the second part separately. And if you take the first part and you can try to make that contribution less than 1/2, and that will give you the capital lambda requirement. I mean, how far up in the spectrum we have to go before we can say anything. And then there is the second part here. You also want to try and make that smaller than 1/2. Of course, you have to be away from the Dirichlet spectrum because it blows up the Dirichlet spectrum. And the reason why we can get a window that is independent of where we are in the spectrum is because we still have this decay here. If we didn't have the 1 over theta down here, then we would have windows that would blow up, that would be larger and larger as the energy grew. So the key is this resolvent estimate here. Okay, so let me start to say a little bit about how to get such a resolvent estimate. So first of all, we critically exploit that this has translation invariance, a discrete translation invariance. So you can do sort of a partial Fourier transform to diagonalize the operator. So here, the inverse partial Fourier transform will go from the sequence space L2 from ZD with values in L2 in the unit cell into capital L2 of the torus, D torus with values in the same space. And if you conjugate the metric Laplacian